Hello everyone, welcome back to class today. Today's topic is going to be hybrid molecular orbital theory. But first, before I dive into what that is, I hope everyone's had a great weekend, and it's nice to see you all again. And let's recall what VSEPR is and just brush up on this. So let's just do a quick example here. VSEPR model for O2, right? So first we draw our Lewis structures for oxygen. We have 2, 3, 4, 5, 6. We have 2 of these guys, right? So how many electrons do we need for a full valence? Anybody? 2, right? Yeah, okay. So we got 2. So we got 2 of these guys. And they both need 2 electrons. This is pretty straightforward, right? Boom. We can create 2 covalent bonds between these 2 oxygen atoms, and then our final model with the full valence shell repulsion theory is going to look like that, right? Where we have our covalent bonds in the middle attaching this oxygen molecule. It's obviously it's linear, right? You'll have the other atoms around it that are going to give it this sort of shape, like methane or something like that. And then we have these extra lone pairs hanging out over the oxygen, and I drew them kind of angled away from the central bonds because of the repulsion of electrons. So now I look at it, it kind of looks like a pair of glasses, but that aside, these models, I find them really useful, they're really understandable, they're kind of cute in the sense that they're very tidy, but there's a whole layer of, what do you call it, detail and nuance here that's sort of glossed over with these models. And that's really where hybrid orbital molecular theory comes into play. Okay, so this is going to take this VSEPR model, which is why I'm writing the S's before the E, but we can't really say VSEPR. Anyway, this is our hybrid orbital molecular theory. So what it's going to do is we're going to take these VSEPR models that we're working with and sort of giving people a sense of what is actually happening with the electrons. Because electrons are not nice little dots. They're not nice little lines. They exist in particle wave format, right? We have orbitals where they have shapes and they fuzz out, right? So this would be like an S one, right? And then we have, this is going to exercise my artisticness. So we have p orbitals, so this would be the x, y, and z axis. And then we have these p orbitals, which kind of belong to these axes. So let me draw this in red, kind of give you a sense of what this might look like. So first we have the x ones that kind of look like that. And then we have z ones that go along the axis here. And then we also have the axis along the y that go along like that. So basically we have these sort of 3 different p orbitals, right? And these 3 different axes that are diagonal shaped. Right? Again, not like these little dots and lines we have in VSEPR. Again, this is really useful to understand very quickly what oxygen might do, but again, it's glossing over some of the details. So, and this is sort of a nice way of summarizing some of that even deeper layer here of sort of the physical chemistry of a molecule of oxygen, which is actually quite complex, right? So, if we're going to describe how O2 is bonded using a hybrid molecular theory, we build up the diagram for O2 differently than with VSEPR, okay? So as the name implies, we mix the orbitals, okay? So we have S, we have P. Each atom has its own S and P orbitals. So we have, hopefully you guys see this down here. So we have like the 1s, and then we have the 3 p orbitals up here. Okay, and this is the 2p. Right? And we have electron here, electron here, electron here, electron here. Okay, and then we have 6 p electrons. Okay, so we have paired up. And this is from, sorry, for clarity, this is going to be 1 oxygen over here. This is going to be another oxygen over here. Okay. Let me divide up the board like that. Okay. Maybe not my finest board work at this moment, but hopefully this will get the point across. Okay. So now what we do is we mix these particles. Okay. And when we mix an S and an S, we create 2 hybrid molecular bonding orbitals, a bonding and an anti-bonding orbital. Okay, so bear with me. This is when we mix these two. These are referred to as the sigma. Okay, right there. And then this one up here is referred to as the sigma star. Now the star denotes as anti-bonding. Okay, so whenever we mix these, the way the physics of the electrons work out is that there's 2 different orbitals right there. There's a bonding and an anti-bonding. Okay? Alright. And now let's start tackling the p orbitals. Okay? So since we have 2 in here, so we actually have 3 different p orbitals here. So we have sorry, these are called pi. So this is going to be 1, 2, 3, and then we have pi, and then we have 1, 2, 3, and these would be all pi star orbitals. Okay? And then we kind of break this up. Okay. This, because when we mix each of these p orbitals, we're going to make another bonding orbital, okay? So, keep going. Okay, and then we just start filling the electrons. So we have 4 electrons total for this one down here. So go 1, 2, 3, 4. Done. That's how it looks for the 1s, okay? So for the for filling up the 2 p's, we're noticing we have 6 electrons here, 6 electrons here, so that's going to be 12 electrons total. So 1, 2, 3, 4, 5, 6. Sorry, I just got confused. I really confused myself. Never mind, ignore that. Right, this is correct. Yeah, 1, 2, 3, 4. 1, 2, 3, 4 p's. Yeah. Okay. So that actually means 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. My apologies. So, right, 4 electrons at the p level, 4 here, 4 here, for a total of 8. Then we fill up these orbitals at pi and the pi star. We have 1, 2, 3 full pi orbitals, and we have 2 and 1 pi non-pi orbital, which comes to, if you add them up, 2 pi. Okay. All right. We'll see you later. Thank you for watching.